Welcome to the second part of Ethernet lower layers. In the first part, we extracted the signal from a network card with the help of an oscilloscope, and we transformed the signal to logical bits with the help of Manchester line code. And in this video, find out what these bits are representing and in general how communication over Ethernet works. Have fun! Okay, here we see our signal, we see the extracted logical bits down here. And now let's have a closer look what this actually means. We see, hey, there's a long frame and it somehow ends at the end. Okay, to check this, let's go back to the browser. Here's the browser, and we have to dig into the details of IEEE on the Ethernet frame structure. This is actually not the physical layer anymore, this is already on a higher layer. And we can see here the Ethernet frame, the structure of an Ethernet frame. You can see the length here and some sample data. Each frame starts first with the preamble, which is 7 bytes and has the pattern hex 55, which is actually very similar, or what is actually what we saw at the beginning of the frame. Then we have a start frame delimiter, which is 1 byte and has the known pattern 5D, hex 5D. Then it continues with the MAC address destination. We will have a look at this at 6 bytes. Then following by the MAC address of the source. So this is actually the sender's MAC address. And here next we have the ether type, depending on which Ethernet frame format this is. We look here at Ethernet 2. So in this case it's hex 800, which stands for IPv4 packet. You can see it here. Then we have the actual payload. The payload in our case, because we are sending with netcat. So this is actually the layer 2. If we go back to the diagram, and netcat will also add an IP frame into it, again with the IP header and a payload. And within the IP header frame, there will be a UDP frame, and the UDP frame will then contain our content dead beef. And this is all here located in the payload section. After the payload, we have a frame check sequence, which is basically a CRC 32, 4 bytes. Here's an example, Affe, this means in German monkey, monkey. And this is calculated starting from the MAC destination address until the end of the payload, and this is the placeholder for the CRC 32. Actually, the frame check sequence is in most of the cases direct calculated on the chip, so on the network card, because this is quite, depending on, especially on the bandwidth, this is quite time critical, and to do this in real time in software is not that easy. Here you find the explanation. We lost, it's not correctly shown here. We have interpacket gap. You can see it here, which defines the gap between the previous frame and the next frame. So if there are, let's say, frames on the line, there's always a gap in between. Yeah. Okay. And if we check here, again, our MAC address, so the sender's MAC address is this, and the receive MAC address is this. And if we go back to, so if we put the two windows besides each other and go back to the description of the Ethernet frame, And then checking our acquired signal, we can see, okay, we have the preamble first, which is a pattern of 05 hex 55, and we have 7 bytes. So let's calculate 1, 2, 3, 4, 5, 6, 7, and then next following the start of frame delimiter, which is D5. Okay, this is wrong on my website here. D5, following by the MAC destination address. Let's see, we have BC 24 11 29, or let's first scroll down. This is actually the destination MAC address. We have BC 24 11 29 6A 4E, so it's exactly the MAC address of the receiver or the destination. If we go back to the frame structure, then it follows by the MAC source address. This is actually this one. Let's check this with the data. We have 00. Let's go there. We have 00 OE C6 BF E8 and 83. So that's good. Then if we go back to the header, we find the ether type. If we look in the description, we have hex 800 for IPv4. If we look into it, we see, I'm just trying to find the right tool. We see, okay, we have 2 bytes with hex 800 here. And then the actual payload starts here with 45. And as I mentioned, there is now the IP header and the IP payload and the UDP header and UDP payload. But let's see if we see our sequence deadbeef within this data here. And here we find it. If you look, we have dead beef within the data. So that means this is the UDP payload. Followed by a view zeros. This is due to that the frame is quite short and this is filled with zeros. And at the end we find 4 bytes which are non-zero, and if we look back to the browser, this is actually our frame check sequence, our CSC 32. Okay, we will now also compare the data or another capture with Wireshark. Wireshark, I'm pretty sure you're aware of. Wireshark is a network analysis tool which allows you to capture the frames, and you can already, or it already parses all headers, UDP, IP, Ethernet, frame header, and so on. And let's quickly add a filter. I add a filter here to only filter for UDP port 8080 so that we don't see all other messages around. And we will capture, and we will start capturing this one. And let's go back to the scope. So Wireshark is armed. We see the oscilloscope and the terminal. With the terminal I will send the frame, but first, so let's see, I will add sleep 2 and then it should send the packet, and I will also arm the oscilloscope. Let's see. Alright, we captured the frame. Let's stop Wireshark and let's have a closer look onto the data. So let me increase the window a little bit, or maybe not. Let me remove, or we will not need the terminal anymore. And let's now compare the different data. I hope the data can still be seen quite well. Let's quickly change to Wireshark. So this is our captured frame. We got an ICMP reply that the target port is not available, but we will just ignore this. And this is actually our Ethernet frame. We see, okay, we have an Ethernet 2 header, which we just discussed previously, and we also saw already on the data. Here as a short reminder, we have the destination MAC, source MAC, we have the type, and then we have an IPv6 packet, which holds the total length, identifiers, protocol, source address, destination IP address, and so on. So this is actually a layer 3 frame, and then the layer 3 frame holds a layer 4 frame, which is here UDP, which also has the source port, destination port. This was the port we were sending to length. It also has a checksum, so that the content can be checked to be correct. And we have the actual data. You can see we have the dead beef. I will now change back to the oscilloscope, and we should see the sequence in the oscilloscope. So if we go back to this window, I hope you can see it. It's large enough. Not sure if I can zoom in here. Wow. Okay, preamble and start of frame delimiter will not be part of. This is already cut off before it gets to the kernel. But here we start with the BC, and if we compare, we have BC 24, 25, 11, 29, 6A, blah 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 blah. We have the Ethernet type, and we have the IPv4 protocol starts here, and if we see, we have 45, 00, 00 again. We have 21B, 45, 40, 00, 40, 11, F3, 6A, OA, 00, 0C, 14, OA, OC, 08, D3, AF, 1F, 90, 0, 0C, 42, DB, DE, AD, and then we have the dead beef. And here we have also, this was actually changed by the kernel, and here we have actually the zero padding and the checksum, which is not part of Wireshark because this is already cut off within the kernel. Okay, what we are going to do now, we will check the frame sequence check and also extract the data. So there's quite a simple method to do this. We just go here to export. We go to Manchester, and we see here we have all the data here captured off. So we will save this as a CSV file. So I just opened this here in LibreOffice spreadsheet. You can see here's the timestamp and here's the data actually. The first line is not of any use, but the others are. What we can do is we can just find and replace age with nothing. Alright, then we see this mess here. We see that 0 bytes have no leading zeros. We will change this in a minute. Let's put this on the right side and then go to format cells. Leading zeros 2. And let's check. This looks quite good to me. Let's take this data and let's just copy this to a terminal. Okay, here we have a terminal open. We just open VI. I don't care. We have I just inserted the data. We have to get rid of the new lines. We will just do this by putting this a new line to an end. Here we have the actual data. Save this as test data and open it. Okay, here we see the extracted data from the oscilloscope after the Manchester decoding. As you can see, we see the preamble here. We have the start of frame delimiter. Here we have the beginning of the destination MAC and so on. So this data, which I marked now, we also saw on Wireshark. And at the end, the last 4 bytes, 1, 2, 3, 4, is the frame check sequence, which I will put extra. This is the CRC32. And what we are going to do now, I will take the data where normally the frame check sequence is calculated, and we'll use an online CRC calculator here, in this case crccalc.com, which is quite a common one. We'll put the input type to hex, copy our data, and go to CRC32. Then we have a look to the ISO CRC32 according to ISO HDLC. This is High Data Link Control. And here we see the calculated CRC. Going back to our data, let's copy it here and remove the hex indication. And we see, okay, it's not quite the same, but if you look, here's the 28, the A6, DA, OE. So this is due to endiness reasons. Here we have the network byte order, where the most significant bit comes, or the least significant bit comes first, and here's the other way around. So if we change this, if we put it like this, then you see it's actually the same. So this proves that the frame check sequence is correctly calculated and appended. Okay, coming to the end of the video. I hope you had fun watching and you could also learn something about network communication. I'm pretty sure you're already using network communication technologies for many, many years. And I hope I could give you some insights how it's working, especially on the physical layer, on the network cable. In one of the next videos, we will also have a look on fast Ethernet here, 100 megabits per second, which was released in 1995, also declared as IEEE 802.3U. And also in another video looking in gigabit Ethernet, declared or released in 1999 and declared as IEEE 802.3AB. There are some differences how this communicates. For the technology shown today, it was quite flexible, quite easy, because we could easily scope the data. What I want to say, we could easily scope the data as we had only a bandwidth of 10 megahertz, and we could easily extract the bits. We will see how this works for the other communication Ethernet standards. Have a good day and ciao.